we'll be recapping here. If memory serves me correctly, and please stop me if I'm incorrect. Current source, all right. In parallel with some resistor R1. And then I had a switch that was closing at t is equal to 0. Then I had a resistor R2 in series with a capacitor, which I called CX, right? And then over here, I had a resistor R3. That was in series with a capacitor that I called CY. Let's see here. So let's call this current ICX, this voltage VCX, this current ICY, and this voltage VCY. That sound about right? Okay. So if memory serves me correctly, the first thing that I did was a Kirchhoff's current law equation, where I said that the current IS was equal to ICX plus ICY plus the current flowing down through resistor R1. Did I express that in terms of ICX or excuse me, ICY? Okay. So let's see, the total voltage drop, because all of these three branches in parallel, would be R3 ICY plus VCY all over R1. And let's play around with that for just a moment. So I'm going to have IS is equal to CX times the derivative of VCX with respect to time plus CY times the derivative of VCY with respect to time plus R3 over R1 CY times the derivative of VCY with respect to time plus 1 over R1 times VCY. And then I could lump things together. So this would look like IX is equal to, excuse me, IS is equal to CX times the derivative of my capacitor voltage VCX plus CY times 1 plus R3 over R1. What's 4? Let me rewrite that. The derivative of VCY with respect to time plus 1 over R1 times VCY with respect to time. And if memory serves me correctly, I reorganize this to say CX times VCX by dt was equal to is minus cy 1 plus r3 over r1 times the derivative of vcy plus 1 over r1 times vcy. Anybody notice any? Oh, I do. That should be a minus sign. Because I'm moving this guy over on the same side as is. So minus there, minus there. All right, so all that checks out. Anybody notice any other algebra mistakes really quickly before we move on to a KVL expression? All right, so that seems okay-ish. Looking at our KVL expression, I'm just going to have the voltage drop across the branch containing CX is equal to the voltage drop across the branch containing CY. So that's going to look like ICX, let me do it this way. R2 ICX plus VCX is equal to R3 times ICY plus VCY. And now I can substitute in for ICX and ICY. So this is going to look like R2 times CX d VCX with respect to time plus VCX with respect to time is equal to R3 CY dVCY with respect to time plus VCY. And then, if my memory serves me correctly, I substituted in this equation into this equation, and that's about where we had left off. So let's do that really quickly. So I have R2 times IS minus CY 1 plus R3 over R1 dVCY by dt minus 1 over R1 VCY plus VCX is equal to R3 CY dVCY by dt plus VCY. Which R3 are you referring to? It shows up twice. This guy right here. So I'm 99% sure that's supposed to be R3CY. So let me double check here and explain, right? So that R3 is for this guy. So R3 times ICY is the same thing as R3 times CY d VCY by dt, right? So this R3 is definitely supposed to be an R3, which was this guy, which was this guy. All of those are correct. Alrighty, so let's see what's going to shake out of this. So I'm going to have VCX over here. And let's do my derivative terms first. So I'm going to have an R3 CY, which is from this guy, plus an R2 CY times 1 plus R3 over R1, which is from this guy right here. And all of that is multiplied by my first derivative term. So we okay with that level of algebraic manipulation? I'm just moving this whole term over to this side of the equal sign, effectively. And then combining it with this guy over here. So nothing is jumping out at me that I've made an error there. Then I am going to have so I have just a 1 VCY over here, so that's taking care of this guy. And then I'm going to have plus R2 over R1. Times VCY, which is me taking care of this guy. Minus IS times R2. And then from this, I should be able to say that the derivative of VCX is just going to be the derivative of this equation above. So that'll give me R3 CY plus R2 CY times 1 plus R3 over R1 times the second derivative. Sorry, this should be VCY here. VCY with respect to time. And then 1 plus R2 over R1 times the derivative of VCY with respect to time. And so now I have the derivative by itself expressed only in terms of VCY. And so what I think I'm going to do So I'm going to see what happens. I'm worried about kind of circular reasoning here, but I'm going to plug it into this guy right here. So that tells me that IS is equal to CX times the derivative of VCX. So I'm going to substitute all that noise in. R3CY plus R2CY times 1 plus R3 over R1. Times my second derivative of VCY with respect to time, plus 1 plus R2 over R1 times the derivative of VCY with respect to time. And so all I've done to this point is literally that term. Now I'm going to add these guys in. So cy times 1 plus r3. I'll just continue on down here. So that was 1 plus r3 over r1. And 1 over r1 VCY. Now I'm going to take this and lump like things together. So I have IS, so let's see, so my second derivative term is going to look like CX, let's put it like this. So I'm distributing this CX in. So I'm going to have R3 CX CY plus R2 CX CY 1 plus R3 over R1 times my second derivative. So before we move forward here, did I distribute that CX correctly for the second derivative term? So all I was doing is moving it in here and here. Okay, so I think I did that correct. Now we're going to have our first derivative term. So I have a CX times 1 plus R2 over R1 plus a CY times 1 plus R3 over R1 times dVCY by dt. And that took care of this part right here and this part right here. Are we all okay with that? Algebra? Oh, that's all right. And then I've got this one last term over here that I'll just sneak in down here. 1 over R1 times VCY. And I have a second order differential equation because I don't want to rewrite all of this noise right here. I'm just going to throw some labels on things really quickly. Okay. So let's call this thing right here lowercase a. This large coefficient here will be lowercase b. And this coefficient right here will be lowercase c. So for this particular example, our alpha should just be b over 2a. Because remember, we wanted the coefficient of the second derivative term to be 1. I just don't want to have to write that huge thing out, so I'm being slightly lazy here, but the process is identical to what we did on Monday. Omega naught would just be the square root of C over what I have labeled as A, where A is just the coefficient of my second derivative term. And so now we would throw numbers in and, see what shakes out. Once again, the hard part of this is always just setting up the second order differential equation. Once we get that done, the problem is literally identical to everything that we've been doing for the last 2 weeks. So, the algebra for that one was pretty damn gross, I'm not gonna lie. Yes, David.
So for this particular problem, the alpha and omega have the A in its denominator, but in like previous sections, those was like B over 2 and square root of C. What makes this different?
The fact that I'm not making the coefficient of the second derivative term just 1. Right? So in all of the previous examples, we set the coefficient of the second derivative term to be 1. Well, when I divide by A, or when I divide B by A, that is setting the coefficient of the second derivative term to be 1, effectively. Or when I divide everything through by A, effectively, it's just setting that coefficient of the second derivative term to be 1. So this is just me being lazy and not wanting to have to write out that big ugly thing multiple times, just for the sake of saving time. All right, so what do you guys want to do now? We did algebra for 22 minutes. Do we want to look at another one of this style problem and work on the algebra kind of thing, or? Yep, okay, so let me make something up. Let's see here. Trying to think if I can do a natural response problem. It doesn't particularly matter. All right, I'm going to give myself a network to work with, and then we'll sort things out from there. So let's call this LX. Actually, we'll move that on the inside. LY like so. Just because I don't want to make this aggressively difficult. What I was thinking about doing, let's make it aggressively difficult. Why the hell not? R1, R2, R3. So I'm just double checking things here. So during the transient condition, I'm gonna have R2 in series with R1 in parallel with LX and parallel with R3 in series with LY. So I don't think this is going to simplify down to just an RL circuit, because I can't sort out how LX and LY would ever be combined. So this should work out to be the right type of problem, at least. Okay, so now let's define some things. This will be my current. I'm just gonna call it I1. And this will be my voltage V1. I just don't want to spend a shitload of time writing extra subscripts when I can define it however the hell I want. And this will be I2, and this will be V2. I'm going to attempt to follow a pretty similar approach where I'm going to do KCL and KVL and just kind of see what shakes out. So let's start with the KVL expression because it's going to be fairly easy. So I'm going to do KVL around the right-hand most loop. And so to me, that's going to look like V1 is equal to R3 I2 plus V2. Everybody okay with that? Now V1 and V2 are both inductor voltages. So I could express, oh, let's change this to L1 and L2 so I don't have X's and Y's and ones and twos all over the damn place. That's just going to confuse myself. So this is going to look like L1 di1 by dt is equal to R3 I2 plus L2, that L looks particularly shitty, di2 by dt. So are we okay with that? Anybody got any questions about where literally any of those terms came from or anything? So the next thing I'm going to do is I'm going to do KCL at this top node here. So I'm going to start with the voltage, excuse me, the current that's flowing through resistor R2. So whatever current that's flowing through resistor R2, I'm going to draw it here in purple, and then I'm going to wind up erasing it in a minute. So we have current flowing through R2. It's going to see this open circuit, can't flow there, so it's definitely going to flow down through R1. So effectively, those two resistors are going to look like they're in series during the transient condition. Okay. The voltage drop across those two resistors is literally just the voltage drop across inductor L1. So I'm going to have, for my first expression, V1 over R1 plus R2. So that's the current flowing to the left out of that node. I have a current I1 flowing out of the node, and I have a current I2 flowing out of the node. And I set all of these equal to 0. And from here, I'm going to substitute in my relationship for my voltage V1. So this is going to look like L1 over R1 plus R2 times the derivative of V1, excuse me, I1 with respect to time. Plus I1 with respect to time will be equal to, let's call it negative I2. Are we okay with that? So I substituted L1 di1 by dt for v1. And then I moved I2 to the other side of the equal sign. That's all I did there. Okay. All right, so I've put it in this form so that I can pretty easily just take the derivative of I2, right? So actually, let me do one other thing here really quickly. I'm going to take the negative sign from the I2 and I'm going to apply it over here. So all I did was just multiply both sides by -1. And you'll probably see the reason for that in just a moment. So the derivative of I2 with respect to time is just going to be -L over R1 plus R2 times the second derivative of I1 with respect to time minus 1 times the first derivative of I1 with respect to time. So I'm going to call this equation 2, this guy equation 3, and we're going to call this guy up top equation 1. And I'm just going to substitute 2 and 3 into 1, and that should give me an expression only in terms of I1. So we would have L1 di1 by dt is equal to R3 times what we have for I2. So that is negative L1 over R1 plus R2 times the derivative of I1 minus I1. And then we're going to have L2 times the derivative of I2, where that is negative L over R1 plus R2 times the second derivative of I1 minus the first derivative of I1 with respect to time. And now everything is just in terms of I1, so it's just time to rearrange things, right? So I'm going to move all of my terms from the right-hand side to the left-hand side to get rid of all of those negative signs. And so I'm going to start, actually, hold on, this should be L1. So I'm going to start with my second derivative term. So that should look like L1, L2 over R1 plus R2, excuse me, times the second derivative of I1 with respect to time. So that's me taking care of this term right here, where I'm just moving this L2 in and moving everything to the other side of the equal sign so that we get a positive coefficient out front. Did I do that part correctly? Okay. Now we're going to worry about our first derivative terms. So on this side, I can see that I'm going to have an L2. So that's from this guy right here. I have an L1 from this guy right here. And then I'm going to have an L1 R3 over R1 plus R2 from this guy right here. So are we okay with that? So I moved this guy over first, which is where I got the L2. Then I included this guy, which is where I got the L1. And then I included this term right here, noticing that there's an R3 out front. So that's why I have L1, R3, R1 plus R2. So that seems to check out to me, times di1 by dt. And then the only term that I have left is just this guy right here. So this should look like plus R3 I1 is equal to 0. And now I could do the exact same thing that I did for the previous problem, right? So if I call this guy right here A, this guy right here B, and this guy right here C, then my alpha would just be B over 2A, and my omega naught would be the square root of C over A. All right, so we did another 15 minutes of algebra. What do you want to do now? You're definitely not going to be given one like that. Like, could we? Sure. Will it be horrifying? You betcha. So I believe, given enough time, I could sort it out, but I don't particularly want to, and I'm definitely not going to ask you to. I might be a dick, but I don't think I'm that much of a dick. God, I've never even thought about that. That sounds the worst. I would probably, I don't even think I do that to you guys in circuits 3, where we were using Laplace domain circuit analysis to make all of this way easier. Even then, I still think that would be wildly difficult. So that just sounds awful. Shame on you for thinking of it. All right. Yes.
You got anything that's gonna be like relevant to the second design project yet?
No. So the second design project is going to be on filters. So we are going to do steady state sinusoidal circuit analysis first. So that's largely going to be a review of the last third of the material that was covered in 221. I'm going to add in a couple of other things that I think are important. Largely, it's going to involve dealing with maximum average power transfer, which is analogous to maximum power transfer in DC circuits, as well as an understanding of how to compute power-related quantities and analyze the circuits that involve multiple excitation frequencies. So it's 70% review, 30% new things, just like, hey, now that we know how to do this, we actually know how to do this too. Then we'll talk about filters for a few days, and that's what your second design project is going to be on. David.
Is there any kind of like, special way where you determine where you want to apply your KVL and KVL?
So for the KCL, realistically, I want a node that involves both energy storage elements and a KVL loop that involves both energy storage elements. Because I need a coupled set of equations that I have to manipulate. So that's why I'm always doing it in roughly the same spot, because I know that if I do KCL at this node, I'm going to have to deal with what's going on in L1 and L2. When I do KVL around this loop, I'm going to have to deal with what's going on with L1 and L2. Exact same thing up here. At this top node, I'm definitely going to be dealing with what's going on with CX and CY, and KVL around this loop forces me to deal with what's going on with CX and CY. I'm wondering now, actually, if we could have made this first problem we could have approached it differently in a couple of different ways that I can think of, just for what it's worth. The most obvious thing is this guy right here could have been replaced with R2 times ICX plus VCX. Would have wound up shaking out to be the exact same thing. What I'm wondering is what would have happened if I had done KVL around this loop or KVL around this loop. And it might have allowed me to put things in terms of just CX or just CY a little bit earlier on. So going around this loop might have made it slightly harder than it needed to be, but I don't think it was particularly difficult. It was just another substitution that we wound up having to do. I don't think you can go wrong per se. It's just, it might not be the most efficient path with whatever choice that you make is. And another thing that we could have done that might have made this one actually significantly easier is there was nothing stopping us from source transforming this guy, which would change the relationship slightly, but we wind up with literally the exact same second order differential equation. Anywho. We can apply literally any circuit analysis technique we want to these because they're still just linear circuits. So whatever helps it seem easier or make more sense to you is completely and utterly fair game. So I think I talked a bit, about this at the end of our last class meeting. I may be misremembering, because my memory is terrible. But for your test on Friday, you should expect effectively to have to work 2 problems of a similar difficulty to the homework sets, okay? So you will have 1 problem that will be a series RLC circuit, 1 problem that will be a parallel RLC circuit. One will involve a dependent source, the other will not. Okay, so that's my expectation of you guys for what you should be able to do for Friday's test. So if you are able to correctly work through homework set 8 and homework set 9, the exam should be a joke because it's the same exact style of material. It's going to be a different circuit and all of that kind of stuff, but it's the same basic thing as homework set 8 and homework set 9. The take-home portion of the exam is effectively just a different problem set similar, or different problem similar to homework set number 10. It's just going to be one of this style of circuit. Okay. So I don't remember what the exam 1 grades were looking like off the top of my head or anything. But typically speaking, exam 2 scores are usually pretty good because it's just the homework problem effectively, but you have to do it 2 of them in an hour and 15 minutes, which I don't think is an insurmountable task. Usually, I don't want to put any pressure or anything, but usually most students finish early. Not saying you have to by any stretch of the imagination, but that's usually what happens. Your best way to study for this is to just make sure that the homeworks make sense. And obviously, you won't be asked to do any LT spice work for the in-class portion of the test. So you don't even have to worry about if that's the thing that's tripping you up. I'm just looking for straight analysis on Friday.
Test.
Test source method, okay?
When do we know which better to use? Or test voltage?
It completely depends on what you're given. That being said, both work. So you cannot do it wrong. It just one might be more efficient than the other. So let me burn through a couple of things here really quick to show you something. So let's say that we had a network, and this isn't particularly related to RLC circuits or anything like that, just in general, okay? So let's say that I had a dependent source here, arbitrarily making it a current source literally doesn't matter at all. Here's some resistor. I'm just going to call this K. IX. So if IX were labeled as this current, really in either direction, the smart choice here would be to make the test source current source because we get to define what IX is. Okay, which makes this dependent source not really a dependent source because we know what it's doing. Okay. So in this particular configuration, a test current source would be best. A test voltage will also work. Now, if our current IX were flowing through the resistor R2, both a test voltage source and a test current source are equally good or equally bad here. So effectively, if you can choose a test source that gives you your dependent quantity, choose that one. Otherwise, it doesn't matter. And realistically, it doesn't matter either way. It'll save you 1 to 2 algebraic steps top. What do you mean by the derived part of the equation? Like the derivative?
Yeah, so you know how I have like y equals this and the other one is dy.
Let me open it up really quickly. 223, probably in the ballpark here, yeah. So we'll just look at this overdamp thing, but the same basic rules are going to apply, okay? So y of t will always either be a capacitor voltage or an inductor current. dy by dt will always be related to an inductor voltage or a capacitor current, because VC is related to IC by a derivative-based relationship. VL is related to IL by a derivative-based relationship. So it wouldn't at all, literally ever. So let me explain what I mean by that by looking at your homework set things here. Let me see. Let me just open up This is from winter, so that should be fine. Open the damn file. So I think this should be probably exactly you guys' homework set, or if not something very close. I don't want to change them too often. So, let's see, I'm not asking you for a resistor thing here. I am asking you for IR of T right here. So let's talk about what that would entail for this particular problem, okay? So I would argue we're trying to find IR of T and IC of T in this particular problem, okay? So since we're trying to find IC of T, we're definitely going to need to know V of T, right? So we would be finding this V of T, which would allow us to find IC of T, but V of T divided by 5 ohms also gives us IR of T, right? So we can't ever solve for the resistor things directly using our system of equations because the resistor does not have a derivative-based relationship associated with it. So we always have to tie what's going on with a resistor back to what's going on with the capacitors and or the inductors. So for this one, IR is just V of T over R, right? When we look at this guy right here, we're trying to find V and IL. So I would argue that we should find IL because V is also the voltage drop across an inductor. So we would just have IL as our first equation, VL as our second equation. We don't need to do anything extra there. For this particular problem right here, I'm looking for IA. I think we worked this one in class. I told you guys a couple of different ways to do it, but how I did it in particular was we found V and then we divided V by the equivalent resistance of this network to find IA. So it was always finding something related to either capacitor voltage, capacitor current, or inductor voltage first, and then using that to determine what was going on with the resistor. That is the only way to work these problems because resistors do not have a derivative-based relationship, which means we can't use those tools. Anything else need clarifying, etc.? Got my attention for another 19 minutes. Could you choose to stay? Yes. Sure, just in general. Alrighty. You care if it's a series or parallel? All right. So let's just do a parallel RLC circuit real quick. So hit me with a resistor value. 5. Hit me with an inductor value. 2. All right, so for this is going to be, I think I said a parallel. So for a parallel RLC circuit, we know that alpha is equal to 1 over twice RC. And we know that omega naught is equal to square root of 1 over LC. We're going to set these two guys equal to each other. So we have 1 over twice RC is equal to root 1 over LC. So from here, we could say 1 over 4 R squared C squared is equal to 1 over LC. I'm going to multiply both sides by C squared. So that's going to get rid of this guy and put a C up here. And now I'm going to multiply both sides through by L. And so we get our capacitor value has to be equal to L over 4R squared if I did this algebra correctly. So that would be 2 over 4 times 25. So 2 over 100 is 20 millihenry. Shit, that's not right. Millifarad. Let's give it the right units. Okay. Just to double check things here. Alpha using that value, let me grab a calculator. Will be 1 over 2 times 5 times 0.02 is 5. Omega naught would be 1 over the square root of 2 times 0.02 is also 5. Yeah, so that works out. Okay. So let's just make this something like this. So 10 volts. Haven't decided on that just yet. Nope, definitely want it opening. Say 2 Henrys, I think. All right, so there's our circuit. So at t is equal to 0 minus, this is going to look like 10. Here's 5. I might need to add another resistor in here just because I think I'm going to have my voltage source shorted out. So I'm just going to sneak another 5 ohm resistor in right there. This is literally just to force this thing to not have 10 volts is equal to 0 volts and break our circuit analysis down. It's not going to have really anything else to do with the transient analysis. That's a short. That's an open. That's a 1 amp source. This will be V at 0 minus. I guess I should have labeled stuff. Sorry. V of t, IL, IC. So this will be IL at 0 minus. This will be IC at 0 minus. So I believe that V at 0 minus has to be 0 volts because it's the voltage drop across a short circuit. IC at 0 minus has to be 0 amps because it's the current flowing through an open circuit. IL will be something else. So to me, it looks like I'm going to have a contribution of 1 amp flowing in from this side and 2 amps flowing in from this side. So those add together to make 3 amps. Anybody got any beef with my analysis? All right, so at 0 plus, the 10 volt source and that 5 ohm resistor are going to be open circuited, so they're not going to be connected anymore. So we're going to represent that like this. Then I have a 5 ohm resistor, I'm gonna have a 3 amp current source direction down. My capacitor voltage was originally 0 volts, right? So my capacitor is gonna look like a short circuit. Here's my 1 amp source. So let's just label some things here. So here's V at 0 plus, IC at 0 plus, IL at 0 plus. So V at 0 plus is still 0 volts because it has to be. IL at 0 plus is still 3 amps because it has to be. IC at 0 plus. So just a quick analysis here. The 5 ohm resistor is in parallel with the short circuit, no currents flowing through that. So we have 3 amps flowing this way, 1 amp flowing this way, so IC is 2. All you gotta beef with that. Oh, shit. You're right, -2. Thank you. Yeah. 1 minus -2 is equal to 3. Yes, thank you for that. Just my inability to do even the most basic addition blows my mind, and I'm sure you guys' mind every damn day. All right, T is equal to infinity. So at T is equal to infinity, same basic configuration that we had at 0 plus, except that now our energy storage elements are at DC steady state. So here's our resistor. Our inductor is a short. Our capacitor is an open. 1 amp source. So here's V at infinity, IC at infinity, IL at infinity. By inspection, V at infinity is 0. IC at infinity is 0. IL at infinity is 1 amp. All right, Jake, because you asked for this, what do you want us to solve for? So V of T and I of L. So, okay, so I'm going to do that by solving for I of L and treat V as an inductor voltage. Okay. So, we have a critically damped circuit where, just to repeat things, we know that alpha was equal to 5 nepers per second. Omega naught was also equal to 5 radians per second. Critically damped, they have to be equal. So we're going to wind up using the values here in a moment. So I could say that IL of T is A1 T e to the alpha T, negative alpha T, excuse me, plus A2 e to the minus alpha T plus IL at infinity. I believe that's correct. I don't have the table in front of me. You guys do, so tell me if I made a mistake. So from here, IL at 0 plus is going to look like A2 plus IL at infinity. Because when T is equal to 0, this whole first term just goes away. So from this, we could say that A2 is equal to IL at 0 plus minus IL at infinity. So at 0 plus, it was 3, and at infinity, it was 1. So the difference between those is positive 2x. Seem okay? All right. VL of T Can somebody look at the tape? Oh, it's right here. Negative alpha A1T. E to the negative alpha T plus A1 minus alpha A2. So VL, oops, sorry. Let me scooch this over here. L times that whole thing because it's L times the derivative. I apologize for that. So that's going to be L times A1 minus alpha A2. So let's see. What was VL at 0? Oh, so V at 0 plus was 0, right? Yep. So if that's 0, then we can just divide both sides through by L. So we're going to wind up having A1 is equal to alpha A2. And since A2 was 2 and alpha is 5, this is going to look like 10. And this should be amps per second. So from here, IL of t will be 10t e to the negative 5t plus 2 e to the negative 5t plus 1 amps. And VL, so let's see, so we're going to have 2 times negative alpha times A1 negative 100 t e to the minus 5t plus, and so now we have A1, which is 10, minus alpha, which is 5 times A2. So that's just going to come out to be 0. Got it done with 4 minutes to spare. No problem. Yeah, so like having a critically damped circuit or an overdamped circuit actually seems like it would be intimidating, but it's actually really good because it lets you have one of your coefficients right from the jump. So in my opinion, the hard ones are when you have an overdamped circuit because you actually have to solve a system of equations.